Okay, so I am going to work one more example problem. This would be similar to what you'd see on a quiz or an exam for the AC steady state circuit analysis that we've done in this module. So here's your circuit given to you in the time domain. We're going to convert it to the frequency domain and then solve it. And I'm going to solve it a couple of ways so you can see a variety of ways to solve this particular problem. So let's start by converting everything. And we are going to, I didn't say it on here, we are going to solve for this voltage Vx. All right, so let's convert everything from the time domain to the frequency domain. Let's start with the sources. So we have 2 cosine 4t, okay, volts. And for our conversion, it's in the cosine form. The amplitude is positive. The angle is 0, so it's in the right range. So this is easy to convert. It's just 2 angle 0 degrees volts. Then we have 5 sine 4t amps. So this is in sine instead of cosine, so we have to convert. So we're going to have 5 cosine of 4t minus 90 degrees amps. So we subtract 90 to convert from sine to cosine. Now we're in the right format, cosine, positive amplitude, the right phase angle, so we can convert this now to 5 angle minus 90 degrees amps. And I didn't say it to start with, omega frequency is equal to 4 radians per second. Okay, so the resistors, 5 ohm and 8 ohm, easy to convert because they stay the same. Okay, then we have our inductor, 2 henries, and that's going to convert to J omega times L. So this is going to equal J times 4 times 2, or this is equal to J8 ohms. And then we have our 0.125 farad capacitor. This is going to be minus J over omega C, which is minus J over 4 times 0.125. And this is going to equal minus J2 ohms when we do that math. Okay, so now that we've got this, we can redraw the circuit, and while I don't always do this, Vx of t, we're going to convert to the phasor equivalent, V hat x. Okay, so, and I've already copied the circuit here. I'm just going to do a little bit of strategic erasing. I'll give you a minute or two to redraw the circuit if you're doing this by hand. All right, so we're going to have 2 angle 0 here. Yeah, 2 angle 0 volts. We're going to have 5 angle minus 90 amps there. So we've just moved those 2 sources over and relabeled them. 5 and 8 are going to stay the same. We're going to have the J8 ohm inductor and the minus J2 ohm capacitor, and we'll have our voltage now, which is the phasor voltage Vx. Okay, and we can solve this using any method that we like. Here, I'm going to solve this circuit a bunch of different ways, and so before I do that, I am going to copy this. Okay, so we're going to start with nodal analysis. So for nodal analysis, we're going to ground that bottom node, and I'll call this node voltage variable V1. Okay, and we don't really have anything in here that we know. Eventually, we'll solve for Vx. Vx is going to equal, we'll go ahead and write that down. So Vx is equal to the impedance, 8, multiplied by the current, and that current is going to be the current that flows in this direction, which is actually going to be in our nodal equation, and it's going to be V1 minus 2 angle 0 over the series combination of 8 plus J8. Okay, and we'll see that again when we write our nodal equation, but that's the current there. All right, so our nodal equation, node 1, starting with the current flowing to the left, again, V1 minus 2 angle 0 over 8 plus J8. All right, plus V1 divided by the series combination of 5 minus J2 plus the current flowing down, which is going to be minus 5 angle minus 90 degrees. And this sums to 0. Again, remember, we don't mind in the equations putting a minus sign on a magnitude, but our final answers have to have positive amplitudes. Okay, but in the middle of this math, we don't have to worry about adjusting that. Okay, so let's do some simplification here. So we're going to have V1 times 1 over 8 plus J8 plus 1 over 5 minus J2 is equal to 5 angle minus 90 plus 2 angle 0 over 8 plus J8. So that's the first step in simplifying. I'm going to go ahead and I'm just going to go ahead and solve for V1. And we'll have, when you do the math here, you'll get that V1 is equal to 21.81 angle minus 90.18 degrees volts. And then when we substitute V1 into our Vx equation, we'll have Vx is equal to 15.49 angle minus 140.42 degrees volts. Okay, and now that we know Vx, we can transfer back to the time domain. So what we want to solve for is this time domain voltage Vx. We only need the real part. So Vx of t is equal to that 15.49 cosine. Our frequency was 4, so 4t, minus that phase angle, minus 140.42 degrees volts. Okay, so that is nodal analysis. Pretty simple. Let's do mesh now. So I'm going to paste the circuit here again. And let's do mesh analysis now. So we're going to have two mesh currents here. Here's I1. Here's I2. All right, and if we start out by writing down what we know that I2 is equal to minus 5 angle minus 90. And if you wanted to, you could leave it like this for the purposes of the math, because this isn't your final answer. But if you feel more comfortable dealing with a positive amplitude, remember all we're doing is a half period shift to get rid of a negative amplitude. So we add or subtract 180. We want to keep the angle between minus and plus 180 degrees. So this is going to be 5 angle 90 degrees. So we add 180. Okay, so hold on just one second. Okay, so that's I2. We can also write down what Vx is. So by Ohm's law, Vx is the voltage drop across the 8 ohm resistor. We need the current flowing in this direction, which is going to be minus I1. Okay, so this will be minus 8 times I1. All right, so we can solve for Vx now, or excuse me, write the mesh 1 equation now. So starting with that 2 angle 0 voltage source, we're going to have 2 angle 0 degrees minus, I forget about Vx, I don't need it for the technique. I've got that series combination, so I'm going to go ahead and combine them. 8 plus J8 times I1. It's on the outside of a mesh. If you want to put minus 8 I1 and minus J8 I1, you can certainly do that if that makes more sense to you. I'm going to do the same thing here for the series combination of 5 and minus J2. So I'm going to do minus 5 minus J2. But now this time the net current is going to be I1 minus I2 because it's shared between the two meshes. and that sums to 0. So again, nothing has changed about the techniques that we're using. We just have impedances and sources that are complex rather than sources and resistors that were all real numbers. Mesh 2 we don't need because we already know what mesh current I2 is, so we don't need this one. All right, so we just are going to deal with this this top one here, this mesh 1 equation. We're going to substitute in that I2 is equal to 5 angle 90, or is equal to minus 5 angle minus 90. Just make sure you're keeping track of your math here. Okay, so let me give you an intermediary step here. So we're going to have I1. So we're going to sum all of the terms here. So we're going to have minus 13 minus J5, J6, yeah, J6, minus J6. And everything else will move over to the right-hand side, and that's all going to sum to 27.73, angle minus 115.64 degrees. And then I1 is going to equal 1.94, angle 39.58 degrees amps. We'll substitute that into our expression for Vx. And we'll get that Vx is equal to 15.49, angle minus 140.42 degrees volts, which is exactly what we got up here. Now, when you're dealing with complex numbers, you might have a little bit more round off error because you're rounding magnitudes and angles, but they should still be really close. And in this case, they're spot on. And so now we can write that Vx of t, the real part, again, we only need the amplitude or the magnitude, 15.49 times cosine. The frequency is 4, so 4t minus that angle, or plus the angle, which is negative, would be a better way to say that, volts. Okay. So that is mesh analysis. Let's do superposition. Okay, and I'm going to paste this again just so we can see it. Okay, so superposition. We're going to let the 2 angle 0 source be on first. Okay, so we'll have the voltage source, we'll have our resistor and our inductor, we'll have our capacitor and our other resistor. So this is 2 angle 0 volts, 8 ohms, J8 ohms, minus J2 ohms, and 5 ohms. Okay, we have opened up the current source. So we've removed it, but that's where it would have been. But we're opening it up when we turn it off, just like we did for DC circuits. And so now we are solving for this voltage here, Vx1, the phasor voltage Vx1, that's a function of only the 2 angle 0 source. Okay, and this is just a big voltage divider equation. Okay, so Vx1, because we have a voltage source and we have a bunch of series impedances. So Vx1 is equal to the voltage source that's available to us, 2 angle 0, multiplied by the ratio of the impedance we want to know about, which is 8, divided by the series combination of all of the impedances in the circuit, and that's going to be 13 plus J6. All right, now, this assumes that current's going to flow in this direction through the circuit because we only have this one source. Current's got to flow from plus to minus, just like it always has. Current's got to flow from minus to plus through the source, just like it always has. So that current's going to flow from minus to plus through that impedance. And so we have to change the sign here so that the passive sign convention will still hold. Okay? No changes in how we do voltage division. So we can solve for Vx1 now, pretty straightforward. Vx1 is going to be 1.12 angle 155.22 degrees volts. Okay, so that's the for the 2 angle 0 source on. So now we're going to have the 5 angle minus 90 degrees amp source on. All right, so we'll have a short circuit where the voltage source was. We'll have our resistor and inductor. We'll have our capacitor and our resistor. And then we'll have our current source. So 5 angle minus 90 degrees amps, 8 ohms, J8 ohms, minus J2 ohms, 5 ohms, and we are solving for this voltage, the phasor voltage Vx2, that's a function of just that 5 angle minus 90 source. Okay, and you can solve for this using any method that you like. I did current division because it's easy, and then did an Ohm's law expression. So this is what I did. I solved for this current here. I'm going to call it I2. Okay, and I did it by current division because I've got this current source here flowing into 2 lumped impedances. One is the 8 plus J8 and one is the 5 minus 2 J ohm, those 2 series combinations. So I can write a current division or current divider equation. The current's flowing in the right direction, current sources. So I've got I2 is equal to the total current available, 5 angle minus 90 degrees, multiplied by the parallel combination of the 2 impedances in each of the parallel positions. So I've got 8 plus J8 in parallel with 5 minus J2. Okay, and then I'm going to divide it by the impedance in question, the impedance I want to know about. And it's not just 8, it's not just J8, it is the series combination of these two. So 8 plus J8, both of those contribute to the current flowing through that branch of the circuit. Okay, so I just have to set this up to solve. And when you plug this into a calculator, you will get that I2 is equal to 1.88 angle minus 136.58 amps. Okay, and if we look back up the original circuit now, I've got, I can write an easy Ohm's law equation to solve for Vx2. It's equal to 8 times I2. The current I2 that I've solved for flows from plus to minus with respect to that voltage. So now I can solve for Vx2 by substituting I2 into that expression. I'll get that Vx2 is equal to 15.04 angle minus 136.58 degrees volts. Now to find the entire phasor voltage, Vx, I'm going to add Vx1 from the first part of the circuit and Vx from the second part, and I will get 15.49 when I add those two polar numbers together, angle minus 140.42 degrees volts. And then I can solve for Vx of t. Again, the same way we've done the other two versions of this circuit. 15.49 cosine 4t minus 140.42 degrees volts. Okay. So Thevenin equivalent circuits are last. Okay, and again, this is our original circuit. Okay, since we're solving for the voltage drop across the 8 ohm resistor, this is going to be our load, and that's what's going to come out. Okay, so redrawing the circuit. Taking out that load resistor and maintaining the terminals. All right, and we are going to solve for the open circuit voltage across that terminal, those open terminals, where we've removed the 8 ohm load. Okay, we can solve for this using any method that you like. I'm going to do mesh analysis here because it's a little different than what we've done before. Okay, so let's look at what the mesh currents are going to look like. So I've got I1 here and I2 here. So what do we know? What do we know? Well, we know that I2 is equal to minus 5 angle minus 90, or 5 angle 90 amps. Okay, so we know that. All right. What about I1? What is I1 equal to? So if you're looking at this and saying, well, we don't know until we write the equation, look a little bit more carefully. I1 has to flow through that open circuit. Remember, this open circuit voltage is just a measurement we're taking. There's not an element here that's creating that voltage. So I1 flows through an open circuit. And how much current flows through an open circuit? 0. So I1 is 0. So you might say, well, what's going on? How can we solve for this open circuit voltage? Well, here are what we know. We know that I1 and I2 are what they are. I2 is determined by the source. I1 is determined by that open circuit. Now let's go ahead and write the mesh 1 equation, noting those two things, because that's what's going to get us VOC. So our mesh 1 equation is going to be starting with the 2 angle 0 voltage source, 2 angle 0 minus that open circuit voltage, minus J8 times I1, minus that series combination of 5 minus J2 times I1 minus I2. And that sums to 0. Sorry to squish this in at the end. All right, so we still have one equation, one unknown, because we know what I1 is. I1 is 0. We know what I1 is. It's 0. We know what I2 is. It's 5 angle 90. Okay, so now we just have to use this to solve for that open circuit voltage. Okay, so just because there's an open circuit doesn't mean that you can't use a mesh equation or a mesh current and use that in an equation. We just know that it's going to be 0. Okay, so one equation, one unknown will solve, and we'll get that open circuit voltage, VOC, is equal to 27.73 angle 64.36 degrees volts. And of course, that is our Thevenin equivalent voltage source. All right, so let me just leave this here for a second because I kind of rushed. Okay, so the next step is to find Z Thevenin. So there are only independent sources in the circuit network, so we can use the quick method. So by turning off all of the sources, so we'll have a short circuit where the current or the voltage source was. Here are our terminals where we're taking our measurement, where we removed the 8 ohm impedance. Here is that J8 ohm inductor, our J2 ohm capacitor, minus J2 ohm capacitor, and our 5 ohm resistor. So we've got 5 ohms minus J2 ohms. We've got J8 ohms. We've opened up the current source. Remember that current source would have been here, okay, but we've opened it up to turn it off. And so now we're going to solve for the Thevenin equivalent impedance that exists relative to those 2 points. And this is very simple because everything is in series. And so we can write that Z Thevenin is equal to 5 plus J6 ohms. Okay, so now we'll draw that Thevenin equivalent circuit. We'll add our load back in, which was that 8 ohm resistor. So this is 5 plus J6 ohms, our Z Thevenin. Here's our Thevenin equivalent voltage. We're solving for this voltage here. Okay, and we can solve this using a voltage divider. Vx is equal to V Thevenin multiplied by the resistance we want to know about, 8, divided by the series combination, which is going to be 13 plus J6, that 5 plus J6 plus 8. All right, now let's look at the passive sign convention here. Current's got to flow in this direction out of the source, so it's going to end up flowing from minus to plus. So we're going to change the sign out in front of that. And so when we solve for this, when we substitute in V Thevenin, which again is the open circuit voltage, we substitute that in, we're going to get that Vx is equal to, no surprises, 15.49, angle minus 140.42 degrees volts, or Vx of t, real part only, is equal to 15.49 cosine of 4t minus 140.42 degrees volts. Okay, so that's all there is to it. Every single time for these. The circuit analysis hasn't changed. We just have to get the circuit in the right format, and then we can solve for. We can use any one of our circuit analysis techniques. We can use voltage division, current division, Ohm's law, whatever we need to solve for the voltages and currents in question. Okay, that's all.